go. All right. So I hope you had a good weekend. Now that people are not, yelling at your ears. Just a little plug for the In Shock fundraiser, right? They're having a jack-o'-lantern carving contest. $5 entry fee. I did get it on good authority that you can have a team. So if you don't want to carve a pumpkin by yourself, but you want to carve a pumpkin with a friend or a group of friends, you can. Just FYI, it was also notified to me that you don't get multiple prizes if you know what I'm saying? But anyway, yeah. So let Mrs. Jolson know by tomorrow if you want a pumpkin, and they will be displayed on October 28th. Super fun. Support your people. All right. Before you get too far into this warm-up problem, let me just say a couple of quick things. So you took a retake of the projectile motion test on Friday. I had just literally saw them this morning, so no, I don't have them graded. I will get them graded as soon as I can, and I will get them back to you as soon as I can. Does that make sense? Don't sweat it. I know, and I'll work on them, and I'll get them to you. Okay, so that's the first thing. Second thing, a few days ago, we had a run-in / conversation about vectors, and my kind of overall decision about how to deal with going through that is that I've got a couple of videos, one that I found and one that I will make. I haven't done it yet, that I will put up on Canvas by the time I go to bed tonight, which might be late, but I will get them up there. So at some point this week, I would strongly encourage you to watch them, okay? Just so that you feel confident about what you're doing as it relates to vectors, but it's not one of those things where we really need to interact. It's more just that you need to get the information. So I'll put them up on a video, and then if you have questions, you can absolutely ask, and we can go through things. But I feel like that is a good solution that won't take a lot of time out of class. We're going to warm up problem today. We're going to talk about tension today. So on the homework for today, I had said to watch the videos that, again, are not quite up there, but they will be. And then these are the problems about tension. You do not have to do all of them today, but these kind of go for today and tomorrow. So today and tomorrow, we're going to be covering tension and making sure that you feel good about it. And then my plan is Wednesday, Thursday, we're going to be doing a lab, reviewing, and then in theory, we're ready for a test over this material, okay? I know that it's been kind of a discombobulated unit, and so I want to make sure that by the end of this week, you're feeling good about it. So if there are homework questions that you have that are kind of still lingering and you're confused about, or if there's anything else that you would like me to know so that I can help make that all kind of fit nicely into a little mystery box so that it makes sense, then let me know and I will help you out, okay? Just communicate with me so that it's not, I didn't know that and I was so confused. This is our opportunity to talk, okay? So you let me know, I'll give you feedback, it'll be great, okay? Questions right now about logistics? Okay, let's do this warm-up problem. I have it larger for you right here, okay? So we have not really met tension yet, okay? But I want you to take a look at this question without having a full definition because I think you can do it just looking at the problem, okay? And then we'll define it and then we'll talk about it and all of that sort of thing. But go ahead and take a look at this question. I'll give you just a couple minutes to think, to discuss, and then we will go through it together. Does that sound good? Tension is a force on a rope. There you go. That's what you need to know. All right. Give it a shot. Have a conversation. You may have realized, maybe not, I don't know, but you may have realized that in this class, I like for you to be engaged with something so that you have something to struggle with so that I'm not just spitting things at you. Have you figured this out? Right? This is how I feel like it's best for you to learn to do this stuff. So let's take a look and figure out what you know so far. So tell me what you know so far. Morgan, you look like you know something. Can you share with us whatever it is?
That the applied force for that F net equals 0.
F net equals 0. Does F net equal 0 in both cases? Yes, it does. What evidence do you have that F net equals 0? It's at rest, which means that it is not accelerating. Okay, so F net equals 0 in both cases, which means that the forces going up and down have to add up to 0, and the forces going horizontally have to add up to 0, right? Do we care at all about the up and down forces in this problem? No. If you were doing a problem that had asked you to figure out the force of gravity and the normal force, could you do that on one of these problems? I don't see a lot of confidence there. Yeah or no? Yeah, there I see a little bit like, so let's go through it for one of them. Just for this second one over here. There's a force going down. Would you guys agree? It's the force of the what? The force of the earth on the block. Also known as FG. It's also Monday, and it's been a while. So if you want to write this down, you absolutely can. Force of the earth on the block. How big is that force? 30 newtons, right? Because that's the weight. It said the weight, blah, blah, blah. And we know it's the weight because it's a normal force, right? It's, excuse me, not normal. It's newtons, which is the unit of force. So this is equal to 30 newtons going down. Just FYI. That wouldn't be part of your free body diagram. I'm just putting that out there. Okay. And is there a force pushing up? Sure it is. This is the force of the floor or the surface on the block. And we might label this as Fn for normal force. Normal means what in this case? Perpendicular, always and forever. And how big is that normal force? 30 newtons. And how do you know that? No acceleration, got to add up to 0, right? So this is negative 30, this is 30, because all of the other forces acting on it are in the horizontal direction, right? We'd put a wrinkle into things if this child, this silly child, was pulling up or pulling down, right? Then things would change. Thankfully for our sanity for right now, the child is pulling directly to the, in this case, the right. Okay. So you got those two forces. Other forces acting? Sure. There's a force like this, right? So this gets a little bit funny. So the thing is that I think a lot of times people get really, really anxious about the tension force. I don't know if it's the name, like tension like makes you really tense or something. I don't know. But I want you all to take a deep breath with me in and out. All that tension is the force of a string. That's it. Like that is literally all it is. Okay? So if you tie a string to something, it's the string pulling on the object. That's all it is. Okay? The fun thing about string is that string is not like necessarily straight, so it can curve, and that's why it gets a little bit more interesting. But literally tension is just the force of a string. So we could argue here that the child is pulling on the string. Are you with me there? And the string is pulling on the box. Right? If the child pulls on the string with 50 newtons, quick question, gut feeling, how much does the string pull on the box? 50 newtons. Does that make sense? Yeah? Yeah. Okay. So this right here, I'm going to put this label over here just because I don't have enough room there. This is the force of the string D on the block. And the force of string D on the block, that's a tension force, F sub T. T stands for tension. If you wrote that as an applied force, that's okay with me. I'm not going to get all crabby about that, but I'm just letting you know that tension is what we call that. Anytime you have a string or a rope or anything like that, that's what it's called, okay? And how big is that force? We just said it. 50 newtons. How are we doing? We okay? So we got the force of string D on the block. It's a tension force, and it's 50 newtons. So now I've got 1, 2, 3 forces acting on the block. Are there any other forces acting on the block, friends? Yeah. What's the other one? The force of the other string, right? So if we're going to label that, and you might want to do that because we're just, trying to be complete here. That's going to be the force of string C on the block. How are we doing? Are we doing okay? Is this kind of making sense? It's also a tension force, Ft. And so you might, if we were doing another problem, we'll do other ones like this, so we'll get there. You could write this as like a force of tension of D and force of tension of C, right? But how big is that force going to be? 50 newtons? In the other direction, right? So you could call it negative 50, or if you're just talking about the magnitude, you just talk about it as 50, right? So it's 50 newtons. Oops. Come on, silly thing. And this one's 50 newtons to the left. How did you know that was 50? The box is at rest, which means that it's not accelerating, which means that the net force is 0, which means that these got to equal to each other. Yeah? So now I'm going to give you about 35 seconds to rank the tension in the ropes. Can you do it? Go. Go, 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 go. At this point, it should be pretty easy, yeah? Yeah. Yeah. Just grab the pass. So did you get it? Oh, go ahead. Question. That's a really good question. Is tension a magnitude? It generally is. Yes. So all of these things, it's going to be a magnitude in a certain direction, and the direction is going to be where the negative or positive comes from, or where the angles are going to come from, which is where all this vector business comes into play. Are you with me there? So in this case, when we're saying what is the tension in the string, you're really just looking at the magnitude. Like how taut or how strongly is that thing pulling? Yeah. Yeah. All right. So have you got some ranks? Did you check with your table mates? You figured it out? Sid, did you guys get an answer back there?
Yeah, A equals B is greater than C equals D.
How do we feel about that? Is that okay?
I like that answer.
Okay. All right. We just learned about a new force. Did you realize that? Look at us. I know, right? That's what I was just about to say. Get that sheet out. Let's add it. I love the fact that you're like, I got that sheet. Oh my gosh, you guys, that just made my heart so happy. Thank you for doing that. All right. Next force on there. Here it is. Tension. What kind of object did we just say? What's pulling or pushing? A string or a rope or something like that. I mean, we're going to be flexible, right? It could be fishing line. It doesn't say fishing line, so it's not. You get the idea, right? Some sort of long, fibrous, you get the point, right? Yeah. I'm going to call it string. You could call it rope. You can call it whatever it is that you want, but it's something that's bendy and that's going to be able to apply a force. Okay? The direction for that force. Is there a way that we could describe the direction? Let me ask you, if the child was pulling up like this, right? So like their hand was up here and was pulling like this, what would the direction of that force be? Would it still be horizontally? No, what would it be? Like up some? How would you describe that? Like it's variable. But if I know where a string is pulling, do I know what direction the tension force is pulling? Yeah, it's going to be pulling away from the box along the string, right? Because away from the box could be like in any direction. But it's along the direction of the string. It's always, and that it almost seems so obvious. Like, duh, of course. But we want to write it down because it's important. Okay, so it's going to be along the direction. That was really poorly written. Let me write that again. Of the string. Okay. How big is it? How big is it? How big is it? Is there an equation for it? No, because you could pull this a little bit, you could pull a lot, right? We don't know. So it's just going to be, it's variable. It varies. For different strings, the maximum varies. I am not an angler. I'm not a fisher person, but I am aware that if you go fishing, you have to get the right kind of fishing line, right? If you're gonna start catching really, really large fish, then you have to have a different kind of fishing line than if you're just catching, little fish, right? Because it has to be able to withstand more tension. Does that make sense? So you have to, kind of like with the normal force, where you have to be able to withstand a certain amount of force, that it will depend, and there is kind of a breaking point, but in general, it does vary. Yeah. Is a tension force able to cause acceleration? Yeah. What evidence do you have for that? Say that again?
I can pull on the string on a box and speed up.
Absolutely. Yeah. Especially, I mean, like, if you imagine this situation without string A, a child pulling on this thing is going to cause it to accelerate, right? So for sure. Yes, for sure. Okay. So yes, of course. Okay. And then for your diagram, I'm just going to draw myself a little mystery box, and I'm just going to draw a little string. And then I would say that the force of tension is right along the string. That's what I'm going to do. Okay. The tension force is not difficult. I think what happens a lot of times is that student physicists second guess themselves, okay? Hey, Bo, will you go close the door? Thanks. Thank you, Eden. There we go. I was like, I'm just gonna leave now. Oh dear. Be safe, my friend. The thing that I want you to know about the tension force is that drawing a free body diagram is going to be the key to your success. Free body diagram, F-net equations, you're going to be good, okay? Don't doubt that, okay? And this sounds silly, but like, don't try to do it without it. Like, trust the way it works because it will work for you, okay? We've got some problems to work here to make sure that this is kind of sitting okay. So we're going to just do a bunch of problems today. And if we don't get them all done today, we'll do some tomorrow. That's how we're going to roll today. All right, so here we go. Oh, that's a lot of problems. I know. Like, if we're going to jump in, let's do it. So here's the situation. Let me explain this to you first, and then I'll give you a little time to talk. More ranking tasks, because you know those ranking tasks make you think, make you understand physics. In all of the cases shown, the systems are at rest. We take that to mean what? Not accelerating. F-net equals 0 all the time. Yeah? F-net equals 0. It's important. In cases A and B, there is a force acting to the right. It's like they stole this from the last problem. They changed some numbers, but this is the same situation. So they just didn't draw the child's hand on A and B. Okay? And it's on a frictionless surface. In case D, let's see, there is a 40 Newton upward force. So somebody's pushing up on this one. Okay? And the task asks you to rank the tension in the rope that's labeled R. So for example, in this one, there are 2 ropes. They only want the force, the tension force here. Okay? More thinking on a Monday afternoon. You're welcome. It's good for your brain. Okay? I'm going to let you guys talk for a couple minutes. I'm going to get some whiteboards out for you. Talk, rank it, and then we will discuss. Sound good? Give it your best. Oh, no. Holy cow. Come back. It'll come back, I hope. Holy cow. Did it come back? So, GE. This is interesting. This is interesting. Did you guys have something right now? Oh, yeah, I looked at you. Okay, so let's take a look at this, friends. Let me have your attention up here, regardless of what you said. Shh. No, I just want to make sure that I'm not saying that you're wrong. I just want to make sure I'm understanding. So I see that there are like 4 different scenarios. Do you guys agree? So let's look at one of each of the scenarios and just make sure that we're kind of on the same page. So for A, what is the tension in the rope in A? 80. What is your evidence for the fact that it's 80 newtons?
Well, it's not accelerating.
Okay, so that means that the
net force has to be 0.
okay.
So it would have to be 80.
Does that seem reasonable? Okay, let's look at C. What's the force in C? Or the tension in C? What'd you say, Drew? 80. Why?
Because if it was less, then the weight would tear it.
Okay. So if I was going to draw a free body diagram, I might have like a gravitational force pulling down. I'm just marking it as FG. And then I've got a tension force pushing up. And those two things have to be equal to add to 0, right? Okay, so 80 newtons there. Cool. All right, let's look at E. Is E 80? I mean, like, I feel like I'm seeing a pattern here. Is E 80 also? What's the value for E? What did you guys say? Or do you know? I don't want to call on somebody. I don't want to call on somebody. Talk to me, friends. 100. Where did you get 100?
40 plus 60.
So that is true. So tell me, why did you add 40 plus 60?
Because, so if there's a weight pulling down at 40 and then there's another weight of 60, they're just going to combine and be one force of gravity on R.
Okay, so I want to look at this and just make sure we're really getting. I think I understand what you're saying, but I'm gonna try and pull out what I like, all the good physics from what you were saying, because like you had good physics, I think, but I just want to make sure we're all there. So if we just look at this one here, what's the net force acting on just that weight? What's the net force? 0. So I've got Fg pulling down, right, of 60, and I've got a tension force here of 60. Does that make sense? Okay, so that's all well and good. Those have to add up to 0. That's all hunky-dory. Now, if I, instead of looking, whoa, hi, I don't know why that opened. Like, that was pretty awesome. If instead of that, what if I had a mystery hanging box? Is that possible? Sure, why not, right? What's the weight of this mystery box with both of these in it? 100, right? So 100 is pulling down, 100 is pushing up, or not pushing up, pulling up so that it can add up to 0. And you told me the tension in here is 60, is that right? Yeah, okay. Okay, so E's got to be bigger than those two then. All right, let's talk about G. Doing the first one of each one. So what did you say the tension was in the rope in G? 160 newtons. Next color, 160 newtons. Where does that come from?
80 newtons on one side, 80 newtons on the other side, and they both can be pulled by R. So together it's 160.
Does that make sense? Okay, but I want to draw the picture. So talk to me about the picture. What's pulling on this one? What are the free body diagram of this weight here? 80 up and 80 down, right? I've got the force of gravity pulling down. And I've got what here? The force of tension, or the force of the string. And I've got 80 newtons pushing down. And what's the tension? 80 newtons pulling up. Right? On the other side, what's the force pulling down on this one over here? 80 newtons pulling down. What's the tension up here? If I cut this string, where's this one going? Down. The net force on this weight has to add up to what? 0. So the net force on this string needs to be 0. 80 down, 80 up. Does that make sense? If this was pulling with 160 newtons, if it's pulling with 160 newtons this way, that means this thing's pulling with 160 newtons this way. Where's this weight going to go? Up. See what I'm saying? This tension force is pushing up. This tension force is pushing up. This is the same force. Are you with me there? Okay. If I cut this one, where's this guy going? It's going down. Does that make sense? If there's 80 newtons pulling down, how much tension has to be pulling up? 80 newtons. Right? I could, instead of doing this, let's imagine that I got that little child that we had from the other one, right? That other example. And I had the child just hold on to the rope here and apply a force in this direction. what force is that child going to pull with to keep this sitting still? 80 newtons. Okay? This is just like a little tug of war, but they're just using gravity as the two pieces, the two sides. Okay? I totally understand why you want to add them together. This is the reason we're doing this problem, is because I want for you to see that this 80 newtons on the left and this 80 newtons on the right don't add together because they're not going in the same direction. Are you with me there? Okay? They're not going in the same direction, so they're not going to add together. The tension in G is not 160. How much is it? 80. Okay? The string only has to pull with 80 newtons to keep this one sitting still. To keep this one sitting still. Okay? TJ wants to ask a question.
Yeah, what if it was, what would happen if it was 0? The rope wasn't falling small.
Then both of them are going to fall.
They're not gonna hold each other up.
Not if there's no string. Like maybe I'm not understanding your question. Ask your question again.
Because they both have they're both 80 newtons, right? So.
They have a weight of 80 newtons.
Yeah,
Mm-hmm.
but they wouldn't hold each other up if the string wasn't. I don't know exactly what I'm trying to ask. So I think.
It's a good thought process, though. Like I don't want you to discount what you're asking,
I think I got it.
because what you're like that's the process of trying to get this. This is a common misconception, which is why I wanted to do this question. That's why I picked it. A, B, C, D, and E, and F are pretty easy, but G is where it gets kind of funny. Okay? The force here and the force here are equal. The tension force pulling this way or this way, it's the same force pulling each way. Tension just transfers force. I'm going to write that on my force inventory, and you might want to as well. The tension force, really, where do I want to put this? I'm going to say in the causes acceleration part, I'm going to say that tension, that force, really just transfers force from one object to another, or to change direction. Okay, like on a pulley. Okay. I'm going to go back to that ranking task, and I want you to fix your answers. Sound good? Okay. I'm not setting you up for failure. I'm setting you up for learning. That's what I want to do, guys. I want you to learn. So take a look at it now. Okay? Process it together. And then we'll discuss it. All right, let's go. So show me some boards so that we can make this thing a reality. So E and then a bunch of things equal and then B and then H. Are we all okay with that? Okay, so E and then a bunch of equal stuff and then, G and then H. So that must be what? A and B and C and D and F. Did I do that right? Yeah? Oh, what did I do? Where did I miss it? What did I screw up? I thought I was just reading your things. Oh, this is G. And this is B, and now it's not in alphabetical order, but you're gonna forgive me so we can move on? Okay. Lena's like, I'm not sure, but we're gonna pretend. All right. Let me figure out what I want to do next. I'm debating here. Yeah, I'm gonna do this one next. All right. Mystery box number 5. Here it comes. Same box. New problem. Now there's a string on the box. What happens when a person pulls upward on the box, as in the picture, with a force equal to or greater than the box's weight? Let's say they're pulling up with 100 newtons. So there's an applied force of 100 newtons on the string, which really means that there's a what on the box? What kind of a force? The one that we just learned about, that we know and love. Tension, yeah. So it's the force of the person, but really it's the force of the person on the rope. and the rope on the box. You with me? Yeah. So I want to know what's going to happen to the box. And by that, I mean, tell me numerically. Can you do that? Free body diagram, F-net equation, solve it. Question, is it going to move? What do you think? Is it going to be at rest? Or is it going to accelerate? Ideas? Thoughts? I'm going to let you think. Yeah. Talk about it. Okay, let's talk and then we'll see how we're doing if we need to add some more information. So I apologize. It's been a few days since we've done a mystery box problem. So a reminder, your friend gives you a mystery box that's 10 kilograms large, right? Yes. And we did this a while. We set it on the table. We found the normal force, right, is equal to the gravitational force. And then your friend came over and pushed on it. And you're like, why are you doing that? I don't know. And then lifted it, pulled it up with 40 newtons. That's where the 40 newtons in this story comes from, right? Like, why would you do that? Again, don't know, but that's what happened. So anyway, the story here is that you've got a force of gravity. I'm going to draw my own picture. I know. Jeez. No, I'm just kidding. I actually didn't, so I appreciate that you told me that. Okay, so you've got the force of the earth on the box, Fg. And you have a normal force this time? Is there a normal force? We're so used to writing about normal forces. Is there a normal force? No, and you can double check that if you go to your force inventory, because in order to have a normal force, you have to have what kind of object? A surface. Is there a surface involved in the story at all? Indeed, there isn't. There's only a string. Whenever you see that there's a string or a rope or a fishing line or a whatever, a thread, whatever that is, you know that it's no normal force involved in that part. It's a what kind of force? It's a tension force, right? So this is the force of the, do they call it a rope? I don't know. They don't call it anything. I'll call it a rope. On box, FT. So we're going to write Fnet, right? Because this is exactly how every single time, and friends, I don't want you to like whine and complain to me when you're doing a test. You're like, I don't know where to start. Because the first thing you're always going to do is draw what? Free body diagram. Second thing you're always going to do is what? Every single darn time. Yeah, right? Whoa. I like that you guys said that in unison. That was beautiful, right? So we've got FT and you've got FG. And does that equal 0? No. The only time we can say it's equal to 0 is if we know that it's not what? Accelerating. Does that mean it's not moving necessarily? It could be moving, but we know that there's no acceleration. In this case, we don't have any evidence to say that it is or is not accelerating. So the baseline answer is just to say MA, right? So you got MA and it's in the Y direction. We got that. And then we know a lot of information here. We know that the tension force is 100 newtons. We know that the gravitational force is 98 newtons. And hey, are they pulling in the same direction? So we got to call one of them negative. Which one do you want to call negative? I'm going to think the gravitational force, whatever makes you happy, but that's what I'm thinking. The mass was 10 kilograms. Again, you may not have known that from before, but now I'm telling you again. All right. Did you need to use an equation sheet for that problem? No, because this is all from the free body diagram and the Fnet equation, and that just all falls out. So 100 minus 98, you got that one? 2. That's easy, we got that. 2 newtons is equal to 10 kilograms, 10 kilograms times A. Can you solve for A? Indeed you can. What do you get? A is equal to? 0.2 meters per second squared. So that is answering the question, what happens? What happens? So your answer would not just be to circle this. What would your answer be? You'd probably write a sentence, and it would say, bam, right? The box accelerates upward at 0.2 meters per second squared, or something like that. How we doing? We okay? All right, cool. Where are we at? Oh, you guys, we got time. I love it. All right, we're going to keep cruising. Is that all right? Here we go. All right, so this problem is a thinker. You're like, we've been thinking all day. What are you doing, Carbling? Yeah, but it's good. It's a good thinker. So here's the situation. Not only do I have one box, now I've got multiple. Woohoo! Want more than one mystery box. I want 2. I want 2 tied together. That's so cool. All right, so the boxes are pulled by ropes along a frictionless surface. Phew, no friction. Tomorrow we'll do friction. You're like, yes! Accelerating towards the left in all the cases. All of the boxes are identical. and all of the accelerations are the same. Okay? So in all of these cases, the acceleration is the same. When they say all the boxes are identical, that really, I mean, doesn't really, the color isn't what we care about so much as the what? The mass of them, okay? The question asks you to rank the tension in the ropes. I'm gonna give you a couple minutes to think because, that's what I do. And that's what you do, is to think. All right, go for it, friends.